Welcome, and thank you for joining the Irrigation Association's 2022 Agriculture Faculty Academy, sponsored by Rainbird and Senator. Before we dive into our second session of the day, Introduction to VFDs, which is a follow-up to our first session, which was Introduction to Pumps, I'd like to take a quick moment to cover a few housekeeping items. So first, I have muted everyone by default, so we won't be disrupted by any latecomers. So please keep your microphone muted throughout the presentation unless you have a question for our speakers, as this will help minimize any background noise. Second, during the presentation, if you have questions, you can ask verbally by taking yourself off mute or via the chat box, which I will be monitoring throughout the session. You can also utilize the raise your hand feature, and I will keep an eye out for that and call upon you that way as well. And lastly, we do want to encourage interactivity, so feel free to have your camera on for the session and to utilize the chat box throughout. You can use it to introduce yourself and share where you teach at as a way to connect with your other participants. So without further ado, please welcome our speakers again, Bill Green and Calmine Vang from the Center for Irrigation Technology. We're going to take over screen share now. Bill, Calmine.
Come back in. There we go. There it is. Okay, thank you. All right, I'm Bill Green with the Center for Irrigation Technology.
And I'm Dr. Calmine Vang with the Center for Irrigation Technology, the acting interim director.
All right, and we want to welcome everyone to our VFD session today. This is a real basic session. We're going to go into talking about variable frequency drives and do some examples of the equipment here. But since we have some new, we assume that we're going to have some new people on today. Dr. Vang is going to start the session a little bit talking about CIT. So we can go to the PowerPoint, please. Okay, you got to maximize it. There you go. Okay. All right. Next one. Oh, I can. There we go.
So we're from the Center for Irrigation Technology at Fresno State. You know, we have a water, energy, technology, hydraulics laboratory, which has been in operation since 2007. As far as CIT goes, CIT has been in operation for over 40 years. We've worked with different organizations and companies throughout the state of California and also internationally. The university itself has applied research on about 1,000 acres, but for us at CIT, we have about 6 acres of research plot that is primarily basically just research. Our farm here with 1,000 acres actually is basically a commercial farm doing dairy. We have multiple different crops such as citrus, almonds, pistachios, and other vegetable crops. One of our most highest selling crop is our corn. And if it's you've been in the area, feel free to taste that. We also have award-winning vineyards. So we have those on our campus. Our primary goal for the Center for Irrigation Technology is 3 pillars: research, education, and testing. Again, we've been doing these for the last 40 years. We have a lot of grant programs and education, which focuses on different topics such as chemigation, specialty crops, and also working with disadvantaged and hard to reach growers. We have sister organizations such as the Water Energy Technology Incubator, and they focus on business development and research and development. When we help them with the research and development portion of that, testing the equipment in our laboratory. The California Water Institute is our over the front door, as we like to say, for the water programs at the California State University of Fresno, but their primary focus is on research, water policy, and education and collaboration. Then now I'm going to give you guys a quick tour of the lab. So since this session is primarily focused on VFDs, I'm going to talk a little about what we have here. We have multiple pumps in this laboratory so that we can hit the different hydraulic features that we're looking for. The lab runs from 0 to 6,000 gallons per minute and also has a range of 0 to 200 pounds per square inch, so PSI. To initiate that range, we have to have VFDs to do the job. So we have a 300 horsepower motor pump here. And then we also have a 50 horsepower motor here, over here on the left, on the right, my left, your, but we also have a booster pump if we needed more pressure here. So what we utilize is we have these big VFDs or variable frequency drives. And when we run the pump and we want to reach different operating ranges, flows, and pressures, that's when we change it. For us, because these units are big, we have an application that we utilize on our phones that we can use to operate the machinery or the mechanism in the VFD. This is all connected through telemetry and or Bluetooth or wireless. So we use it on our phone, and we could control everything that's happening in the laboratory. We also have a 50 horsepower VFD, and this one controls the smaller pump. And that way we can move water based on how small or how large we need to do volume of water. In our laboratory here, we have a sump here, over here, behind where the pumps are. It's 22 feet deep. It's about 50,000 gallons. And then of course our different pumps. But the way VFDs work is based on hertz or frequency, but then that translate into rotations. So here you have temperature, that's the temperature of the water in the sump. And as we move faster or the pump goes faster, the rotations go faster and you get a higher reading on your rotation. And that's kind of the idea behind VFDs. The more frequency, the higher the frequency, the faster the rotation goes. And that's how you get your VFD, your RPMs to change. So that's why we have this, so that we can measure the rotation and the speed based on what the frequency is for our VFDs. This system here that we have here is actually built around a actual pump test facility that's located here in town. This is a newer version of that, and so we built this around that. But also, this facility is also represented in the Mobile Education Center. Basically, the Mobile Education Center is a small version of this. The crazy thing is we have a 50 horsepower motor here, but we can power it with the solar panels on the ceiling, and that's how we can generate enough power to power that without using any electricity from the grid. So, and then we're going to go back to the Mobile Education Center. Okay. So the overall arching goal of our program, which is the Advanced Pumping Efficiency Program, which is part of CIT, which is one of our larger programs. The Advanced Pumping Efficiency Program has been in operation for over 20 plus years, and we have tested over 30,000 pumps and also put on over 400 to 500 workshops within our time. Now, the overall goal is to save energy and water, so water use and energy efficiency. Our objectives are to assist with helping farmers find and get more efficient pumping systems, especially hardware, into the field so that they can do their job to the best of their ability. And the second objective is, of course, to make sure we're managing these systems and utilizing them efficiently so that we can maintain that energy and water use efficiency. So what do we offer? The APEP program, or Advanced Pump Efficiency Program, offers subsidized pump testing for motors and pumps over 40 horsepower. We provide a $100 rebate for each test that is tested, each pump that is tested, and for smaller booster pumps, in-series booster pumps, we provide a $50 rebate. This goes for every 2 years or so. This program has been going on for over 20 years, so we've done over 30,000 pumps. We also provide assistance with cost analysis. So after getting a pump tested, we can work with the grower to identify how or how much money they can save by changing their system or making it more efficient. And we also try to help them make good decisions. And then we provide technical support. We have a staff here of Kayla and JJ and Bill Green and myself. And if you guys needed help, or a grower or a farmer needed technical support or identifying their how they can change their system to be more efficient, we can help them with that. And lastly, education, of course. our education program has been going on for 20 years. And again, we travel all across the state of California, and we've even gone outside of the state of California. The furthest we've traveled, of course, Bill has driven this mobile education center all the way to Florida and back. So we travel and we go different places. But our education is also primarily within California to provide water use and energy efficiency. And this is our contact. So if you wanted to contact our main office, this is our information. Feel free to call us at the 1-800 number. And then if you want to reach me, Bill, Kayla, or JJ, this is our team for the Advanced Pumping Efficiency Program. Feel free to reach out and we can answer any questions that you guys would like to.
All right. Let's see if I got my, yes, I am on. I guess thank you, Calmine, appreciate that. And you saw the VFDs and the tour of the lab there. We have VFDs on our demonstration trailer here too. So I'm just going to talk about a few things about pumps just for a minute, because some of you may not have been on the earlier session when we went through this stuff, but I'm not going to spend a lot of time. When we're talking about pumps, our program of pumping efficiency, it's called overall pump efficiency, or OPE, and we're getting the flow rate, the total dynamic head, and the energy in off the smart meter, or in this case, off of our VFD, gives us kilowatts in, and we can convert it to horsepower in. So that's how we're going to be getting our efficiencies today as we're running these VFD and this equipment behind me. And I'll give you a quick tour of that in a minute. We talk about flow rate. We're talking about gallons per minute today. It could be cubic feet per second. That's just conversion. We know that you get that through, we get that through flow meters. And we have a flow meter on our trailer here, and I'll give you the tour here in a minute to show that to you. We also talk about total dynamic head, which is the total lift of the pump. And I just wanted to show this diagram. We're having to calculate how much pressure or lift we're using to move the water up this hill, get friction through the pipes, and have pressure at the end. All that is calculated, and we convert pressure to feet by multiplying by 2.31. If you had a container of water 2.31 feet deep and you look at the pressure at the bottom, it'd be 1 psi. So that's how we convert pressure to feet. And so you'll see our pressure gauge run in a little while. Here's an example real quick. I showed this earlier again, 10 foot of suction lift, 190 foot of elevation lift. It's not to scale, obviously. To convert friction losses to feet, we go 20 psi times 2.31 equals 46. And pressure maintenance, 60 psi times 2.31, 139 feet. So in this particular equation, or this example here of total dynamic head, or total lift of this pump from the water to here to run the sprinkler system, we're going to have 385 feet of lift on this pump, or feet of head. Okay, so that's just one thing I wanted to show real quick, because we'll be utilizing that. And so it's important to understand that. And then based on that, we have a pump curve, because you'll see the pump curves I'll have on here. And that pump curve shows that combination of lift in feet and flow rate down here. So for example, this is the pump curve here. So example, at 500 gallons per minute, where it intersects on our pump curve, it's about 80% efficient. That's impeller efficiency, not overall pump efficiency. That doesn't include the motor and stuff. That goes into it too. And about 145 feet of lift. You go right on the curve, you see the flow rate goes up, say to 700 gallons a minute, now to 100 feet of lift, but our efficiency dropped off. If we go left on the curve to 300 gallons a minute and maybe 170, 175 feet of lift, you see our efficiency's dropped off, but that's more lift or more pressure, less flow, but always a combination of those two things with the pump. Now with the VFD, it allows us to manipulate that curve quite a bit and change the characteristics. This is always at full speed, this curve right here. But if you use a VFD, you might slow it down and get some other examples. So, and we're also getting energy in readings off of our smart meter. We'll come back to that in a minute because I'm going to show several examples. We don't need to show it right now, but we're using, that's the other thing. So we're getting flow rate, total dynamic head off of our equipment, off our pressure gauges times 2.3, and we're getting energy in through the smart meter, and actually through our VFD gives us energy in. So that's one of the advantages. So we can do continuous pump efficiency. And with the VFD, we can show how that's being affected too, because VFDs don't necessarily make pumps more efficient. They just make them they can use less energy when you don't have to run them full speed. And that's the whole point of a VFD. And so we'll have the MEC running, and we'll show you pump curves, we'll show flow through the flow meter, we'll show pressure on the gauge, and then we'll convert it to feet of lift or total dynamic head. Your OPE will be shown, and we'll be doing some examples with a VFD with a variable fluctuating table. And I'll show you how a VFD can sometimes help overcome that. And some farmers here in California are now utilizing that, especially when they have a variable water level aquifer that changes levels. So before we get to this first one, let's do our quick tour of the MEC for those of you that weren't on the earlier session. We're going to go ahead and go to the big screen here, and I'll show you what we have. Okay, first here, first I should show the whole thing. Basically, we have our whole pumping system here. We have a water tank up front. Water comes down through, runs around through the piping, and then comes back this direction, down through this lower piping, through this valve here, and back to the tank. We're pumping in a circle. Same thing that what lab, that's what Calmine mentioned. This is a small version of our lab, which is a bigger version of it. That sort of thing where we're pumping a circle, because we're not, ordinarily the water would be going on out to the field for irrigating crops. We're not doing that right now. We'd run out of water real fast if we did that. So because we don't have a deep well or something supplying us. So that's what we're doing. So let's start here on this side. We have our tank here that is a water tank right here that is filled up with water. And we have our smart meter there and our 2 VFDs. We'll be coming back to those quite a few times here through our demonstrations. We have our pump right here. It's a submersible pump, 5 horsepower submersible that has one of the VFDs that's connected to that. The other VFD is connected to an end suction centrifugal pump we have on here too. So we have separate VFDs for each one. But I think because of our limitation on time today, we'll mainly be using this pump. Water comes out of that. We have our chemigation valve, so backflow prevention, low pressure drain, air vacuum relief vent, and single mainline check valve. You have to have those in agriculture if you're injecting fertilizers or pesticides. We have our pressure gauge here with a transducer. There we go. And that transducer takes the signal of pressure to when I have this pump running, you'll see the pressure reading. You multiply that by 2.31, and that gives you feet of head. So we'll see how many feet of head are coming out of this pump. Water comes on down the curve here as we move down, comes around the corner here like this, and then comes back, and we have a second pressure gauge here. And this is if we're running this booster pump right behind me here. I can divert the water and run it through the booster to create extra pressure. So we can see how much more pressure is being created by this pump versus the pressure being created out of the other pump. So that's called booster pump or end suction centrifugal pump, horizontal centrifugal. It's got a few different names anyway. Water moves on down here to our flow meter. And the flow meter has a propeller here that turns. And if I can change this, close and open and close the valve right here and change the conditions, it'll change the amount of flow. And it'll change the pressure on our pressure gauge, and all that can be shown. And we can do that with a VFD without even closing the valve. We can change our characteristics of our pump. So that way, this is basically a pressure regulating valve here. It's a hand valve, but it can still do pressure and flow regulation. We'll do it with our VFD, a lot of our examples instead. We may do a combination with both to show what happens with efficiency and how VFDs work. And then finally, we get back again to our 2 VFDs here on the close-up. And one's for each pump, and you can see it shows the hertz that's going to run there. You can't really see it very well. Oh, let's see on the screen there. I ran this one already. This one pump is ready to go right now. It says 59.985. It's basically 60 hertz. It's full speed when I'm running that pump. I haven't run the other pump, so it doesn't show anything today as far as the VFD goes. So that's basically our system. So we can go back to the full screen here. We are pumping in a circle, and we're going to be manipulating the pump using our VFDs and changing the speed on the pump shaft. So let's go through that real quick, back to our PowerPoint. And again, if there's any questions or comments along the way, please feel free to chime in, and I'll try to give you as much information I can. Oops, sorry. I always grab the mouse here, and that takes Kayla's ability to change the screen. All right, so what is a VFD? Variable frequency drive. Well, variable frequency drive is one name. Variable speed drive, same thing. Adjustable speed drive. You hardly ever see this term anymore, but they're still used a little bit. Usually we call them VFDs because it's just become the kind of the go-to, but any of these are the same thing. And it basically changes the rotational speed, how fast that shaft is turning from the electric motor, say, going to the bowls and impellers. And we change that speed. Normally, pumps run at full speed. This gives us the ability to throttle the pump down. And when we do that, and I'll explain this in a little bit, that can save a lot of energy. And so that's why they've become very important in agriculture. They're being used in a lot of places, and there's a lot of different ways they can help you in running your system. So again, here's the pump shaft here. If there was a shaft on the bottom of this motor, we're changing the rotational speed of this shaft here like that by throttling down to run that VFD. So if we don't need full speed, that changes the horsepower equation and changes things so that it changes how much energy is being used by the VFD, or by the pump, I should say. So it allows you to automatically throttle. It can be done automatically or it can be done manually. I'm going to do both actually here. I'll set up two different examples of an electric motor, just like you would a diesel natural gas engine. In fact, when I was in farm management many years ago, I still manage my own family farm, but when I was doing large scale farm management, I had a lot of natural gas and diesel engines because as we harvested our peaches and nectarines and plums throughout the season, and we didn't need to irrigate as much post-harvest because we had different varieties that came off different times of the season, a lot of times I wouldn't have to irrigate as many acres. And so if the pump was running full speed, it'd still be using the same amount of energy and it would be giving me too much flow. Well, I could throttle down those diesel or natural gas engine. I'd burn less diesel and it would help, save money. Well, the same thing at that time, this is 20 some years ago now, there really VFDs weren't coming back into play very much in agriculture yet. Now they're becoming very frequent when you have those kind of conditions where you have different size blocks, different emission devices, different flows and pressures, basically. We don't need full speed all the time. Slow the pump down, saves a lot of electricity. So that's what it does. It also can be easy on the machinery. Soft starts will demonstrate that. There are trade-offs. They cost some quite a bit, although the prices in many cases have gotten more affordable, especially on smaller horsepower, but even on bigger horsepower, they've come down a lot. They used to be about $400 per horsepower. So if you were going to put a VFD on a 100 horsepower pump, it might have cost you $40,000 to do that. Now, a lot of times you can get 100 horsepower done for less than 20,000. But you just need to do your research on what's the brand you want to use and make sure you get a good quality brand, not an off brand that nobody's heard of. There's quite a few different brands out there that are very good. There is power quality considerations. There's uneven voltages off your power lines or through your transformer. Surges can trip the VFD. It can cause problems with your pumping system too. The VFD can correct some uneven voltages if they're not real bad, but if they're real uneven, if you got 483 phase power, let's say, and one leg you got 540, one leg you got 410, the other leg you got 460, that's uneven voltages. And the VFD might be able to straighten that out a little bit, but that might be too much and it might trip the VFD. And that'll help keep your motor and other equipment better for longer because you can talk to your power company, your power supplier, and say, hey, we need to get this voltage issue taken care of. One of the things I'm going to talk about right now is harmonics and harmonic distortion a little bit. I got a few slides on it because PG&E and California is having terrible time with this right now, and it's going to get worse with all the solar energy being produced in the state. With all the VFDs, you've got changes in the power being used at different locations constantly, and it makes uneven voltages and other issues happen. Those harmonics can occur and can trip the VFD or cause damage to your pumping system. So there's all these things to deal with too, and I'll talk about that later. Also, for physical restrictions, VFDs are not real fond of 100+ degree temperatures out in the field. If it's dusty and dirty and all that, a lot of times you have to put a cooler on there to make them work properly. And so certainly they have to be encased in a box with a fan and with a filter and stuff that has to be cleaned periodically. There's a lot of little things with VFDs when you put them in that you got to deal with, but they can save a tremendous amount of energy in the right situations. If you have no reason to run other than full speed, they're not going to save you any energy at all. In fact, you're going to lose about 4% efficiency through the VFD. But if you're as long as you have a reason to slow that pump down part of the time, it can save tremendously, and we'll demonstrate that. They are usually, if you have widely varying operating conditions, different flows and pressures, maybe you need high pressure, low flow, or low pressure, high flow, on a consistent basis, then they come into play pretty good. So they're very common on municipal water systems because obviously there's a different amount of customers pulling water out of the systems. Here in Fresno, we have 250 deep wells approximately running the city of Fresno, and they have VFDs on some of their pump stations. They also have multiple pumps. So they can make their pressure vary by turning pumps on and off. But golf courses, it might be you're irrigating fairways, roughs, or greens as opposed to the approach or something different speed, maybe different amount of water. Maybe you have a drip system on part of it. Sprinklers on part and drip system. You don't need all that pump energy all the time. You can slow that pump down. Dairies and their vacuum milking systems use them a lot. And now agricultural packing and processing plants are using them there. And I should just put on here, agriculture irrigation is becoming very common in many cases to have a VFD. So what can they do? There's a lot of things we're going to demonstrate here that they can do. And I may have to come back to this list. If I've forgotten something, I'll remember to do it. First is a soft start. They'll wind up the pump slowly. You know, usually when you start a pump across the line, just hit the switch. It's in a split second, it's full speed. And there's takes very much an inrush of current off the transformer. They have to oversize the transformer, in fact, to give you that extra current to start the pump full speed. And then after a split second, that doesn't require that anymore. But the transformer can be more costly. So especially on big horsepower pumps, I think over 400 horsepower now, you're required to have a soft start here in California. I think this is pretty common across the United States because they don't have to size a huge, gigantic transformer. They can use a smaller one. Just wind that pump up slowly. You can set up to wind up in a few seconds or slowly over minutes if you want with a VFD or with a soft starter, but we're talking about VFDs today. During that time, a lot of times you'll get some cavitation when you do across the line starts, especially with booster pumps and things like that. It's good to have maybe start it up slowly so you don't get that cavitation and could damage your impellers. So soft start can help with that. I've seen it help with reduced well sanding. If you have a deep well that's producing a lot of sand as you're pumping, maybe especially when you shut it off completely. I've had wells that I had this way before. When you first start them up after they've been shut off for a couple of days or something, man, they pump a lot of sand for a few minutes. And then you got filters plugged and all kinds of problems. You got to flush and go crazy. If you can soft start it, sometimes that'll reduce some of the sand. Also, a lot of ranches where they've had major issues with this, they'll keep that pump running at a lower speed all the time, and it never shuts it off completely. And they're pulling very little horsepower when they do that, and they're able to keep sand from being an issue. Sometimes you oversize the pump horsepower because you have a variable or fluctuating water table. This is becoming more common in California, where farmers, the water table has been dropping with the drought quickly, and they're having to pull their pump every few years and put a new one in because they have a new condition. Well, what if you oversize that pump, put it in once, and maybe it lasts for several more years because you've got enough extra pump there and you run it slower? I'll demonstrate that. Different irrigation sets, emission devices, acreages, elevations. You know, if you have different hills and stuff, even with your setter pivots and stuff, maybe they want to run different volume of water sometimes on certain times of the year and things. There's a lot of reasons why maybe slowing that pump down and running less water at certain times might help you and have less runoff on elevation and hillsides and things like that. But you want to maintain system pressure. You preset your RPMs to create flows and pressures you need. You can do all that. And of course, if backflush or filtration systems, sometimes I've seen VFDs where when you go into flush mode, a lot of that water is being diverted from the irrigation system. And while it's flushing, you're losing a lot of water, and it's affecting how your irrigation system is performing. Maybe you're getting poor uniformity at that point or something. And if you have extra in your pump there, it can run slower. And then when it goes to flush mode, it speeds the pump up, and you can still get the same flow going to your field. So you have a nice even application of water going the entire time. That can be something that it can help with assisting with the backflush too sometimes. There is issues, especially in California, but I imagine in a lot of places, it gets pretty hot out in the field. And so you have to have an enclosure, and you got to run maybe an air conditioning unit or something like that, especially with bigger horsepower VFDs. Some of the new VFDs can handle up to 150 degrees. So if you encase them with a fan and stuff, they'll be pretty good. But a lot of times they'll be even better if you do enclose them and cool them. Problem is, it costs money to cool them. And so that's working against your energy savings, the fact that you're running the pump slower. Maybe because they have to be in the whole system has a lot of dirt and debris and dust in the field. You want where your pump station is, you want to close it. You have to clean that filter periodically. And then, of course, we've mentioned power quality issues like surges and spikes and voltage issues and harmonic distortion, where you get that feedback through the line, and it's almost like a wave coming back from the shore that goes back and can blow up a transformer or something like that on a power pole. And this is becoming a major problem with all the solar and everything. You know, you got a cloud goes by, and you got all the solar being produced, and it causes changes in the amount of energy is produced very quickly. A cloud blocks the sun, and all of a sudden those solar panels aren't producing. So in that area specifically, you could have an issue that goes along with that. So very important to pay attention to that kind of stuff too.
Hey, Bill, I just wanted to kind of interject here quickly too. We do have a hand raised from Charles. So Charles, if you want to take yourself off mute and ask your question, it'd be great.
Hey, Bill, Charlie, Abby, how you doing?
Hey, Charlie, good to see you. How are you?
Good to see you. Doing good.
Good.
Hey, quick question on on the VFD, is there a limit as to how slow you can slow a VFD down?
That's a good question, Charlie. Yeah, actually, one of the things, maybe not the limitation of the VFD so much, it's a limitation on your pump motor. And a lot of times, I didn't even mention this because we didn't have a lot of time today, but you have to maybe put different windings in your pump motor. Your old motor might not be set up because you may run hotter, especially if you run that pump slower. You remember that pump, as it's rotating, that motor, it's pulling in air through the vents, through the fins or whatever they're called there, and it's cooling itself. And when you start slowing it down, it doesn't cool itself as well. And so the old standard was you can only run half speed. So if 60 hertz or approximately 1775 RPMs on a lot of pumps, they vary a little bit from make, but on a vertical turbine, a basic pump, if you're 1700 and 1800 RPMs and you slow it to 900, that's half speed. That would be going from 60 hertz to 30 hertz. That is usually to make sure you don't void the warranty on your motor. You may have to have that limitation. However, I'm going to point something out here in a minute, how much less horsepower you're pulling. And maybe if you get it down that far, that should be enough anyway. Some of the new VFDs and electric motors, I understand, can go slower than that now. They're being rated down to, say, 20 hertz or something like that, where you can go even slower. How much? 300 RPM. Thank you. Calamine just chimed in. They're helping me there. 300 RPMs. So that means you could go quite a bit slower. At that point, you'd be pulling very little horsepower, and I'll explain that here in a second. And hopefully that answers your question, Charlie, because you're absolutely right. There is a limitation, at least that's on there. But the old standby was no slower than half speed. Now the new ones, a lot of times, can go slower than that. So if you have the right equipment, just make sure you do. If you have one of the older VFDs or something, they may not want to. I think that would be, especially if you run it over extended period of time, no load on it and things, that's when it comes into play on that electric motor mostly. Won't hurt anything on the pump, the bowls and impellers or anything, I don't think so. All right. Now, this is a pump curve, and I'm going to show you this because it shows different RPMs. Now, this pump motor with a VFD only is at 1500 RPMs is a full speed on this motor. And you can see as you slow the curve, it makes separate curves for each RPM. I can do this with our demonstration here in a little bit. And you got down, and you see down here at about half speed, which is 700 RPMs is the lowest rating here. And that's probably because they don't want you to run it slower than about half speed. So that shows you what happens with the VFD. It gives you a lot of big operating condition changes. You see the flow rate down here goes from 0 to 5,000 gallons a minute. Well, look at point C, you're at 4,000 gallons a minute. At point D, you're only at 2,500 gallons per minute. Point A, you're at 3,200 gallons per minute approximately, but you've got about 80 feet of lift. If you go over here to your feet of lift head, if you only need 3,000 gallons a minute with 20 feet of lift, you go to point B here. It gives you a lot of range here that you don't get. Usually you're on the curve, full speed with the pump, and you're limited to that. Other than, slowing the pump down with a pressure regulating valve or something, which can be very inefficient. And we demonstrated that earlier sometimes. Anyway, so this gives you a lot of range. And you notice these are efficiency numbers here. It says 80, 75, 70. And you see these lines that flow across, these brown lines that flow across, shows how efficiency goes. On this pump, if you slow it down here to this point, which is about 2,800 gallons a minute with about 30 feet of lift, you're at 84% efficiency. It's actually gained efficiency. This is impeller efficiency, not overall efficiency. So you see it spreads these efficiencies out, which helps you. However, if you're running way over here somewhere, let's say you're running at 1,000 gallons a minute with 40 feet of lift right about here where I got my cursor, at that point, you're only 50% efficient. You're not very efficient. Now, does that mean it's a bad idea to run there with a VFD? Not necessarily, because even then, you've slowed that pump down to 900 RPMs at that point, right about here. 900 RPMs, and so you're running much slower speed. You're going to save a lot of horsepower. Now, the reason for you save horsepower is what we call the affinity laws, and it's a set of relationships for turbine pumps only. And these all in the booster pump we showed, the in-suction centrifugal, the submersible, vertical turbine, those are all types of turbine type pumps. So basically it takes brake horsepower, which I think I have my next slide here. Brake horsepower is from the shaft down, not including the motor. Okay, so it's just the pumping plant itself with the shaft. The brake horsepower, it takes brake horsepower A divided by brake horsepower B equals RPMs A. So the RPMs on the pump shaft divided by RPMs B, the difference cubed. So brake horsepower equals brake horsepower A divided by the RPMs difference, A to B. So A would be maybe full speed, say 1800. I got a number right there, 1800 horsepower. Let's say our brake horsepower is 100 horsepower. I got 1800 RPMs at full speed on a pump. I slow it 20% to 1500 RPMs. The difference is, it's not a straight line savings. It's the difference between these two cubed divided into the original horsepower, which would be equivalent to about 58 horsepower. So I slowed the speed 20%, but I decreased the horsepower by 42% in this example, over 40%. That's why VFDs, when you slow pumps down, can make a big difference. And let's see right here on our chart. I didn't point this out originally on our chart, but you see these different speeds, different pump curves here. Look at the horsepower. This is a 100 horsepower pump, right at 5,000 gallons a minute right here with about 70 or 80 feet ahead, something like that right here. We're pulling a full 100 horsepower, full speed. You slow this pump down to 1350, now you're only pulling 75 horsepower. So you decreased it by 10%, decreased the horsepower by 25%. You go all the way down here to half speed, 750 or so, right about in here, you're only pulling 15 horsepower out of that pump. So now it is really tremendously pulling a lot less energy to create whatever conditions are you need. So instead of having to run full speed and regulate it with a pressure regulating valve, you do use a VFD to slow the pump down and save a lot of energy. And that's the whole point of VFDs. If you have a reason to slow that down, they'll save energy. If you have no reason to slow it down up here, they actually cost you 4% more energy because of the inefficiency through the VFD. And you can buy a soft starter if all you need is a soft start cheap. Most people, the VFDs are not that much more now than soft starters, so they buy this. Yeah, they maybe they're a little bit more, but they buy a VFD because it gives them other options. Maybe they don't need full speed all the time. At my farm, my little 20 horsepower pump runs full speed, irrigates the whole field at once. If I put a VFD on, it actually costs me more money. Plus, not to mention the cost of the VFD. I have no reason to slow it down because I irrigate everything at one time. So it just depends on your application. But remember that people think, and I've had examples of this, where they put a VFD in, think it's going to magically save them energy. And they look at their bill and they don't see them saving any energy. If anything, has gone up a little. And they've come to me and asked, why not? And I said, well, how are you running it? And they said, well, I run it full speed all the time. That VFD is going to save energy. I said, no, it doesn't. It only slows it when you slow the pump down. It only saves it, I should say, when you slow the pump down. Go to a different RPM, lower speeds. Okay. Yes. Do we have a question? Ooh.
Let's see. We do actually have one that came in.
Vertical blue lines. Okay. Well, that's net positive suction head, and it has to do with cavitation and the submersion of the pump in the water and stuff. You have to have positive pressure or head on the pump of a certain amount. And you notice as you get to higher flow rates, that number goes up because you have to have your pump submerged greater or you could have cavitation. And that's a safety. And you know, that's why these pump curves stop right here, because they don't want you to run in this area over here because you could start cavitating and damage your impellers, cause pitting and stuff. So that's called net positive suction head. And so that's a different thing. I can't say that I'm a super expert at it, but I kind of understand the idea. You have to have that pump submerged or have enough positive pressure into it so that you don't get cavitation. And that's what those blue lines indicate. Hopefully that answered the question. Might be an interesting class for some other time. It's very important when you're designing your pump. So, okay, so I'm going to start doing some examples on the MEC here. We're going to describe what we're doing. How are we doing here? Oh, we're running out of time as usual. I'm going along with it. So we better get going. Is that okay? 20 minutes. Okay.
Yeah.
And of course, my computer always shuts down.
And if you need to go over a little bit at the end too, Bill, I mean, I think that's okay. And people can jump off if they need to.
Yeah. These things always take a little more time than I think. So, okay. Let's bring our thing up. I'm just going to probably run the one pump today because we don't have enough time to do it. I'm going to start it right now. Now, let's I want to do this twice here. I'm going to show a soft start. So I'm going to start the pump and you'll see it, and I'll describe what's going on, and maybe you can close up on the flow meter. So here's our flow meter here. It's not even turning yet, and you'll see it start to wind up. See, there it goes. Open it up a little bit. Okay, now it's turning fast. You can see it turning there faster, okay? The flow meter's turning, but it was a soft start, okay? So it took several seconds to go from 0 to 60, I guess you'd say, or 0 to 60 hertz in this case, because we're running full speed right now, okay? That's what a soft start is. Let's do it one more time. Now, let's go to our chart here now, Kayla. Now, I'm going to show you our chart here. And what it is, right now we're off, pump's not running. I'm going to highlight this down below, and I'm going to hit the start button right here, this green arrow down at the bottom there. Hopefully you see that. And I'm going to hit this, and you'll see the flow and everything start out, and then it starts coming up. Ah, I got to close this valve, forgot. Okay, so that was a soft start. Now it's up to full speed, and we're right on our pump curve right there. Just to go over this real quick. This is our pump curve here. We got flow rate on the bottom, 0 to 200 gallons a minute. Total dynamic head, 0 to 140. Right now, we're running about 106 gallons a minute, 107. You see our numbers are bouncing around with about 89 feet of lift. That 89 feet, we're getting off of our top pressure gauge up there, Kayla. There you go. It says it's running about 38 PSI. I bet if you multiply by 2.31, that equals about 89, 90 feet ahead. 38, 40 pounds pressure, whatever that is. Pretty close, okay? So our flow rate's running about 106 gallons per minute. Our TDH is 89, and our efficiency right now is running about 56%, which on this system here is very good. Okay? So that's kind of your basic showing the soft start. So that's the first thing I wanted to demonstrate. You can buy a soft starter without the VFD that can do that for a little less money if all you need is a soft start. Let's say you have a 400 horsepower, big giant pump, and the power company goes, hey, you can't, our transformer won't handle it. You have to have a soft start, wind it up slowly. You could do that. Now, again, the soft start could help with sanding issues and other issues, cavitation, things like that, so you don't get issues going on. Also, water hammer through your piping. When you start a pump at full speed and it's there in a split second, you can hammer the pipes. I've had pipes blow up before in the field because we didn't have proper ventilation or something, and all of a sudden you had a pipe blow up, and I had a pipe just rip open out in the field before, PVC pipe. So all these things are important. The soft start can assist with that. Okay. All right. Let's go back to the PowerPoint for a second. I'm going to leave this running. So reduce water hammer, reduce cavitation, particularly when they'll cross the line start. Oh, I got the wrong. I got to get the different mouse here. Sorry about that. And reduce RPM can reduce well sand issues. I don't know if I count that unless you know for sure it can, but I think in many cases, when you don't have to shut your well down completely and you don't get that sand build up and you can run it real slow, you can keep that sand issues from occurring. I've heard that people are doing it successfully with that. Okay, let's demonstrate first a variable or fluctuating water table. Now, you see the diagram here. You got your static or standing water level. You turn the pump on, it draws down to the pumping water level. And this is the lift in feet to the surface we have to do. But if this static level goes down, then the pumping level will go down. If the water level comes up, the pumping level goes up. And so that means you're going to get different flow rates. If you go back to your pump curve, you get different flow rates out of there, which may mess up your irrigation system. If you only need a certain flow rate through the season, maybe you want to put, and the other thing that's happening now in California with the drought is these water levels are changing quickly and mostly going down, and farmers are having to pull their pumps out, put a bigger horsepower pump back in. So a lot of times it's cheaper to oversize the pump a little bit, put a VFD and run it slower. And I'll do a demonstration of that right now. Let's go back to our chart. All right. So I'm going to do it right on this chart to start with. I'm going to start out. I'm just going to do this manually. Now I can do it manually. If you look at my cursor here that's moving around, on the bottom here is the RPMs right here. I could plug in 3,000 RPMs and manually slow this pump down. Let's see what it does. Now, our pump slowed down. You can hear it probably. Let's say we only need about 100 gallons per minute. I'm going to fix it here so it's about 100. There we go. Let's say we need 100 gallons per minute. Right now, we've got that. We didn't need all of our speed on our pump, so we slowed it down. Now, I should have showed you the energy signature, and I may go back and do that real quick. In fact, let me speed it back up. I'll show you something real quick. Sorry, I forgot something. Okay, let's get a close-up on our meter. Sorry about that. I want to show you how much, at full speed, how much energy we're pulling right now. Okay, that's our meter on our trailer right now. That's kilowatt hours. Here's kilowatts, 4.66 kilowatts. Now I could do the equation. You divide by 0.746 and that equals horsepower. It's about 6.1 horsepower, I believe. So our 5 horsepower pump is pulling more than 6 horsepower because of the inefficiency of the motor. But basically, we're pulling about, let's just use kilowatts. Right now we're pulling 4.65 kilowatts. The numbers bounce a little bit. Now I'm going to slow it down 20%. Let's see how much we're using. Not to mention that was giving us a flow rate that was too high on our pump. We only need 100 gallons per minute. So we're going to let it scroll through here for a minute. First number hasn't shown it yet. I just slowed the pump down. And we're running about 100 gallons per minute like we want now. Now we're pulling, it's coming up now as it scrolls through on our smart meter. Now we're pulling 2.78 kilowatts. So I slowed the speed from 3,600, now 3,600 RPMs on this submersible pump is full speed, to 3,000. I sold it 20%, but our kilowatts went from 4.65 to, what's it say again? 2.78. I slowed the RPMs 20%, but I'm saving about 40% plus on the energy coming into the pumping plant right now. That's why VFDs can save money, because of those affinity laws. And those are kicking in. And I'm still getting the 100 gallons per minute I need on our pump. Let's go back to the other screen, please. So we're getting our 100 gallons per minute about right there, 99. I'll try to fix it so it's 100. Pretty close. All right. Our efficiency's dropped off a little, but it's not bad. And we only have it 50 feet ahead because that right now our water levels have come up. So what happens, I'm going to mark that spot right there. Now, let's say the water table starts dropping. The aquifer level is going down, variable or fluctuating condition. I'm closing this valve to mimic that condition. There we go. Now, you notice now we're not getting 100 gallons a minute. Well, you can set your pump up by changing the RPMs to automatically. Let's go to 3,200 RPMs and see what happens. Oh. I'm doing this manually, kind of guessing at it, but it's close. All right. I don't know why I'm doing that. There we go. Okay. So now we're back up to our 100 gallons per minute again. We're getting adequate. I messed up my thing a little bit, but there we go. Let's do that again. That's close enough. So we're 100 gallons per minute. Now let's say the water level drops again. And the pump speeds up some more. 3,400 RPMs. And we're back to our 100 gallons a minute. Okay. Finally, the water level keeps dropping down. And the pump speeds up again. Now, this can all be set up to do automatically. 3,600. And we maintain our flow rate at all times. It's supposed to be a straight line, but it's pretty close. You get the idea, okay? Now we're at our full speed. There's nowhere to go from there. But every time I increase the speed, the energy into the pumping plant increased too through the VFD. Now we're at full speed again, and we're pulling 4.69 kilowatts, back where we started, even a little bit higher because there's more pressure or something. Anyway, we're back to where we are. Now we're more efficient, but every time we do this, the cost went up because we're having to create that extra pressure. This is kind of an example of what guys are doing. Now, if the water level starts dropping again, the pump slows back down. And hopefully we're maintaining our 100 gallons a minute or something like that. You get the idea. So the point is, for a variable or fluctuating water table, the pump can speed up and slow down. Okay, this is just one example of how a VFD is sometimes being used here, so growers aren't having to pull their pump out every few years and put a new, bigger horsepower in because the water levels keep dropping. You oversize it, hopefully maybe it'll last for 10 years or something after that, and you don't have the investment. And if the water levels, if we get a wet winter and the water levels come up, it'll slow the pump back down and save you energy. So it's a little bigger investment up front, but it's very costly to pull pumps in and out all the time. All right, that's one example. Let's go back to our PowerPoint real quick. I'm going to leave that running.
Yep, and a question did come in, Bill.
Okay.
About in the industry, are farmers expected to know how to program a VFD, or is that an installer job?
No, normally it's installers. You have to set up the parameters your irrigation system requires, which I'm going to do an example of now, showing how they'll set up a certain discharge pressure or something that you want to meet all the time. Maybe you have multiple flows and pressures. They can set this up in the VFD under different programs. But I usually you're going to set up, if your irrigation systems, generally speaking, they're going to be irrigating drip systems, maybe different size blocks or something, or different elevations. They're going to try to have a same discharge coming out, or a transducer that tells you what pressure I need to meet, and the flow rate just automatically falls out of that depending on how many blocks you got running or whatever, up to full speed of the pump. So the farmer could learn how to do that, but I think most of the time you're going to have a professional do it. The books are thick. It takes a while. They're getting a little easier to use as time goes on. And when we first started using them 20 years ago, I was with them out here and we're trying to program these things. It was kind of a nightmare because we didn't know what we're doing. And there's a lot of little specs. Even on I have a VFD on my pool pump at home. And because I have these laminar jet things and stuff my wife wanted to install. And I play with it all the time, changing RPMs just because it's fun. And I've learned how to use it. But the farmer's not going to have time to do that. So he's going to get it pre-programmed probably most of the time. Let's do another example now. I'm going to go to a different screen. Now, what's key? Yeah, I know I'm going to run a few minutes over, I'm afraid, again, because there's just no way I can do this.
No problem, Bill.
What's key is understanding what we call the load profile. What different flows and pressures do you need? Or do you need a certain pressure all the time with a different flow rates? Because maybe you have different size blocks, or you want to run half of it and not the other half part of the time, or whatever it is. Because you got new plants out there, or different crop, or whatever. You can set up your system to do this, and we're going to set up a load profile on our system now. So let's go to the big screen. Oh, I got to clear that off. There we go. I'm going to have to limit. I have a lot more demonstrations. The problem is we're not going to have time to do them all. So I'm going to do just a real basic one here. I'm going to say that we want to maintain about 60 feet of total dynamic head. What? Oh, I thought you said so. 60 feet of head. See, I put it on there. It's bouncing around a little bit, but it's about at 60 feet, which is equivalent to about 26 pounds of pressure on our pressure gauge. Okay. So I'm going to set up a low profile automatically to keep that feet of head. Now I'm going to set it up first, the different flow rates that we need to run based on our different blocks using a pressure regulating valve. And I'll use my valve to do this first. And I'm going to set up this profile at that point. So at full speed, and I'm going to set it up. I'm going to go ahead and put all my curves here. I have different speed curves for different speeds here, as you can see. All right. So you see 3,600 RPMs, 3,200 RPMs, 2,800 RPMs, 2,400 RPMs, okay? Show how the efficiencies fall across it and everything else. I'm going to set up this first condition as our number one condition we need is 129 gallons a minute. So with or without the VFD, the cost is about the same. Our numbers bounced a little bit, but you get the idea. They're the same. Actually, that's not actually true. If you needed this condition all the time, the VFD is costing you 4% more because of the inefficiency through the VFD. But let's say, let's just ignore that because we're using a VFD. Let's say it's 25 bucks, and this is per acre foot right now. With or without the VFD, that's what it's going to cost us at 19 cents a kilowatt hour at that point. And I'm going to mark that spot. Now I'm going to figure out what other flows do I need, just to give you an idea of a load profile for the system. And I can only set up 3 with this profile. You could do online software, could be quite a bit more than that sometimes. I'm going to move this valve. Let's put it right about there. Let's say we need about, that's about 90 gallons per minute, I think. I'm going to say this is without a VFD now. This is with a pressure regulator. I'm going to put that spot down and show the cost. And it's costing us $35 an acre foot at 91 gallons per minute. You see our numbers bounce a little, but you get the idea, okay? I'll come back and do the VFD example afterwards. Let's do our third example of a flow rate. We'll give it about 55 gallons per minute or so. Its numbers are bouncing around, but that's pretty close. I'm going to set that point. All right, and it's costing us $54 an acre foot. That's because of all this extra pressure. I'm going to mark that spot too, though. So there's our 3 points we need to create the flow rates we need: 129, 91.4, and 53.7. You get the idea. Now I'm going to use a VFD to do the same thing. Set at 60 pounds pressure, because we have all this extra pressure we're burning off in that pressure regulating valve. So I'm going to open this back up. All right, we're back basically where we started. Again, with or without the VFD at this full speed port, it's about the same cost, okay? But now I want to match up my flow rate, which is this one right here, with this flow rate right here, and plug that point in, but I want to maintain 60 pounds pressure. So I go down to the bottom here, and I highlighted the thing that said 80 right now. I'm going to plug 60 feet of head in there, not 60 pounds pressure, sorry, 60 feet of head. That's about 26 pounds pressure. That's going to be our number that we stay on. All right. And then I'm going to click this hold button right here. And then I'm going to go back to my valve, and I'm going to start showing, I'm going to match up that flow rate with the other condition. Hear the pump slowing down? Now we were pulling about 4.6 kilowatts. Now we're slowing down, and it'll show the RPMs down there, how much they're slowing down. And I'm trying to match up the flow rate here. It's hard to hit it perfect, but oh boy, I might have nailed it. No. It's hard to hit it perfect, but I'm pretty close. I'm going to go with that. A little bit more. There we go. There we are. Let's mark that spot. All right, I hit it perfectly. Look at the cost difference. With a VFD, instead of $35.66, it's costing us $21.57 per acre foot of water pumped. Okay, so that's a pretty significant savings. Look at our RPMs. It went from 3,600, which was full speed, right here, I'll highlight it here in the bottom, down to 3,020. Now, all I did was change the block to a different block or something that required less flow rate, and it maintained that system pressure automatically. Now, I did it by closing the valve, but that's all we're talking about doing there. And that's what kind of savings you're talking about. Let's match up the other condition. And it's slowing the pump down more. You see, it's going to stay at 60 feet ahead. Now, this is not reacting super fast because we have it set up that way. It can do a lot quicker reaction. It can react within a matter of a second or two. Let's see if I went too far. I might have gone too far. There we go. Close enough. It's not going to be perfect, but we'll get close. Oh, I hit it pretty close. Let's see what the cost difference is at this condition. At 54 gallons per minute, it's only costing us $24.61 instead of 53. Our RPMs has slowed down to 2,700 RPMs. So we were at 3,600, we're 900 less. That's 25% less RPMs. Let's see how much energy we're pulling. We were pulling 4.6 kilowatts. Go to the close-up on the meter, please. Let's see it scroll through here. We might have to let it scroll through twice, but it says 2.0 right there. Let's see, that'd be about 2.5 horsepower. Let's let it scroll through again. This number doesn't mean anything. Then you got kilowatt hours. That's the total you pay for every month that goes up, and you pay that to the power company. Kilowatt hours times your rate. Yes, it's running at 2 kilowatts. 2 kilowatts, and it was at 4.6. So I slowed the RPMs from 3,600 to 2,700. That's what it's running now. Let's go back to our other screen. There you go. It was running 3,600 RPMs. Now it's running 2,700. So that's 25% less RPMs, but the more than half of the horsepower is not being used now. The Affinity law is kicked in. Big savings on this. Then you can go further. You can do more analysis. Well, what percentage of the different water am I pumping here on our load profile? Let's say 40% is this amount here. 30% of the water I'm pumping is here. 30%, that adds up to 100. So then if you know that you're pumping, say, 500 acre feet for the season, or let's say 600 acre feet for the season with your pump, I didn't put the cost of the VFD in there, but on your electrical savings alone down here at 19 cents a kilowatt hour, that's an off-peak cost in California, you're going to save almost $8,000 in electrical costs. The VFD and a pump system like this would probably cost 10, 12 grand. And there's rebates through a lot of power companies, especially here in California and stuff, so it might even get a 1-year payback on a VFD. If you have a scenario like this works very well. What about if you have a scenario where 95% of the time you're full speed, or 90% of the time you're full speed, 5% you're here, 5% you're here. Now you're going to save about $1,200 a year. And if that VFD costs you 10 grand to put in, that's going to take 8 years to pay it back, 9 years. Then it's debatable. If you're 90% of the time you're full speed, maybe you're just a little less efficient the other 5% on those other two conditions. That's just an example. So it depends on how much water you need at those different conditions. But this is a pretty extreme example. There's probably fits somewhere in between. And a lot of people have a greater load profile than this they need to set up. There's actually VFD companies have software online. You can put in different flows and pressures and show things like that. And they can show you what kind of savings you can expect on your system. So anyway, I kind of think I'm out of time because I went 5 minutes over and I didn't get to do about half the things I can do with this thing, but that's the way these talks go because we only have an hour. So is there any questions or comments along the way?
I don't see any additional ones in the chat, but if anybody wanted to ask me last minute questions, feel free to speak up now.
Well,
okay, I think we're good. Any other kind of closing comments before I wrap this up?
No, I just think when you're going to evaluate VFDs, make sure that you check with the manufacturers. I mean, there's a lot of off brands coming out of, well, I won't say what country, but the country that sends us a lot of off brands, and a lot of those debatable how good they are. So you might save a few thousand on your installation, but put a cheap one in, and then it doesn't work right, or it fails after a short time. These VFDs ought to last for many years. Now, if you have to change your motor horsepower and stuff, then sometimes you have to change the VFD too. If your old motor is not made for a VFD, you may have to change the electric motor on your pump. That gets expensive. But a lot of times these systems were being put in with new pumps, and they're just retrofitting the old system, realizing this could work. And it also makes the thing I didn't talk about at all is how much system control helps with your staff. A lot of times with these complex irrigation systems and stuff now, different flows and pressures, the irrigator that's out in the field may not really understand what different flows and pressures he needs and have a hard time regulating his valves to create that. So it affects your uniformity of your irrigation system and other things. The VFD takes a lot of that guesswork out if it's set up right. And if you have reasons to slow that pump down, it can really be great. So hopefully
one question did come in, Bill. So
okay.
From Charles, where are the best resources for VFDs is your question, right, Charles?
At least for agriculture.
Bill,
I'm sorry, Charles, go ahead.
Oh, hey, just wondering, like, where would be a good place to find more information on VFDs? Is lots a good resource, or?
Well, we aren't really a resource for that. We have several brands in our lab alone here. I mean, we got Danfoss on the trailer. You got a GE. I think you got a ABB or Allen Bradley or something. There's all kinds of brands out there. Yaskawa, Telecommunique, all these different brands. I think I'd go on their websites and get some information, but also I would try to talk to an engineer or a pump company, pump designer. Most pump companies are installing a lot of these now, and so they're getting more and more involved with it. And I work with some electricians down your way in Visalia. Actually, they did some work on your system out there. They are pretty good resources. They deal with these a lot, and so they should be able to help you some. But depending on what you're trying to get, if you're educational information, that's a good question. I don't have a lot more than what I just gave you here, but anyway.
Great.
Awesome. Thank you.
Thanks for the question, Charlie.
Yep. And then I guess to just kind of close this out real quickly, excuse me, my voice is a little under the weather here. But so again, just thank you to the CIT team. The presentations were great. We really appreciate your support for many, many years for the Faculty Academy. So thank you to both Bill and Cowmine to kind of lead that for us today. And then tomorrow, our next session is the basics of fertigation and chemigation and regulatory impacts with Jake LaRue. So that session begins at 12 p.m. Eastern time. Zoom reminders for both the 12 o'clock and the 2 o'clock session will be sent out tomorrow morning, similar today. So if you're joining, please be sure to use those links for tomorrow. And then I think before we want to conclude, I just want to point out a couple opportunities for you all as educators and some of your students. So IA's Irrigation E3 program is now accepting applications, just opened. So this is an opportunity for students and even faculty to attend the 2020 Irrigation Show and Education Week in Las Vegas, which will be held in December. So please take a moment at some point to check out the IA website for more information on that. And then lastly, just to call attention to the fact that IA does have a number of teaching kits and student workbooks available via their website and store. So academia receives special pricing. There are about 20 topics. So again, worth a quick perusing when you have a little bit of time. So that's it. So again, thank you everyone for joining us today. And again, a final thank you to our sponsors, Rainbird and Senator. So have a great day, everybody. And thank you everybody for participating.